Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 15, Part 2, Latin squares design. All right, so overall, if we want to use the Latin squares model, we're controlling for two different blocking factors, and it kind of looks like the Sudoku setup where our treatment shows up once in every row and every column. Okay, so we had those slightly two different notations. So depending on which notation you're using, you can use what I have written in black or what I have written in blue. You can find estimates of your parameters, and then using those, you can find your fitted values, right? Or you can also find your residuals. And the way you do that is by using the equations here. So our y hat ijk's are equal to your mu hats plus your tau hat k's plus your beta hat i's plus your gamma hat j's. And just like always, if you want to find a residual, you're going to take the observed minus the predicted value. And at the end of the day, our residual EIJK is equal to YIJK minus Y bar dot dot K minus Y bar I dot dot minus Y bar dot J dot plus 2 Y bar dot dot dot. From there, we can partition the total sum of squares. And remember, the reason for partitioning the total sum of squares is so that we can set up our Anova table. So the source for the Anova table is going to be the treatment, the rows, right? The blocking factor for the row, the blocking factor for the columns, the error, and the total. So remember, there's T treatments, and in this case, the degrees of freedom would be T minus 1. For the blocking factor for the rows, remember, we're also going to have T values for the rows. So our degrees of freedom, once again, is T minus 1. And then we have the blocking factor for the columns. But remember, there's T treatments, there's T columns, so we have T minus 1 again. And then we have the error and the total. We can get our sum of squares due to treatment. And this is our main concern, is what is the effect of treatment after controlling for two different blocking factors. So that's why we're only calculating an F value for the source of treatment, because we're really not curious about what's the effect of the blocking factor. We are only interested in saying what's the effect of the treatment after adjusting for the blocking factor of the rows and the blocking factors of the columns. So we're going to use this Anova table to test the quality of the treatment means under a Latin squares design. So when we do this, we can state our null and our alternative hypothesis by saying HO is the effect of each of the treatment T's equal to 0, or HA, not all of the tau i's are equal to 0. Essentially, what we're going to do here is we're going to calculate our F statistic, which takes our mean square for treatment and divides it by the mean squared error. Our F statistic should follow an F distribution with corresponding degrees of freedom. And what we have here is a skewed right distribution that peaks at 1. We can set up our rejection region and our fail to reject region. And essentially, this is the value for which we would say that we have enough evidence against our null hypothesis to conclude that we believe that at least one of the treatments means is different from the rest. So we're going to set up our rejection region by putting alpha in that upper tail. And when we do that, we're essentially saying that our type 1 error, we might reject our null hypothesis when the null hypothesis is true, alpha times 100% of the time. Okay, so to get our critical value, right, we could do QF right? And we could put alpha and then put our degrees of freedom 1 equal to t minus 1. And our degrees of freedom 2 equals to t minus 1 times t minus 2. And when we do that, we're going to get the F value associated with that area, right? You could also use the F tables to do this. Essentially, you would go to the correct degrees of freedom 1 and 2 in your book, and you go to the alpha level, and then you'd figure out what the F critical value was from there. To calculate our P value, however, you're going to calculate your test statistic, and from there, you're going to do PF, and you're going to put in your test statistic here. And then your degrees of freedom 1 is going to equal t minus 1. Your degrees of freedom 2 is going to equal t minus 1 times t minus 2. And then you're going to say lower dot tail equals false, because essentially your p-value is the area greater than your test statistic, right? So you want the upper tail, not the lower tail, and that area there is your p-value. Now, there's nothing so special about a particular alpha level being 0.05. We're just using this as a threshold to decide when we're going to reject. So a p-value of 0.049999 is not really that different than 0.050001, right? The p-value is just telling you how much evidence you have, and the smaller and smaller it gets, that means the more and more evidence you have against the null hypothesis. So we can compare that p-value to the alpha level. And if the p-value is small, we'll reject HO. And if it's large, we're going to fail to reject HO. But what does this mean? Overall, if we have a lot of evidence against the null hypothesis, so our test statistic is very, very large, we're going to say that at least one of the treatment means is different from the rest. Whereas if that F ratio is close to 1, we're going to say there's not a significant difference in the treatment means. So in the next video, we'll do an example and we'll be able to walk you through it. See you next time.